So before we can understand permutations and combinations, we first have to understand the fundamental counting principle. Say, for example, we have 4 people, and we're just going to name them A, B, C, D. How many ways can we arrange these 4 people? And this is by assuming that we're selecting every single person. So each set is going to come with 4 people. So if we were to arrange these people, we'd start off with 4 options for the first spot. And now for the second spot, we only have 3 options left. And then for the third spot, we'd have 2 options. For the last spot, we have only 1 option. Because in the first spot, you can select for any of the 4 people. So let's say we just chose A. Now A's gone. So for the second spot, we only have 3 options to choose from. So let's say we choose B, then that's B gone. So we're left with 2 options for the third spot. If we choose C, then we're left with 1 option for the last spot, which is D. So we're going to multiply this, and we're going to get 24 ways of arranging. That's called a factorial, and we write that as 4 with an exclamation point. So 4 factorial equals 4 times 3 times 2 times 1. But for this kind of counting, we're assuming that we're using all of the items, and we're not just selecting a few from them. And also, order matters, because if we were to have A, B, C, D as a lineup compared to A, C, B, D, that would be different, and we would count that as another lineup. But what if you don't want to choose all 4? What if you just want to pick 2 out of the 4? That's where permutations and combinations come in. So for permutations, the order matters, meaning that A, B, C, D is considered different than A, C, B, D. These count as 2 different arrangements. And that's the main difference between permutations and combinations, is that for permutations, order matters, but for combinations, it doesn't matter. So the formula for permutations is NPR equals N factorial over N minus R factorial. This is outside the parentheses. N refers to the total amount of things from the group that you're choosing from. So for an example, if you have 5 students and you're trying to pick a team, then N equals 5. That means you have 5 options to choose from. It's the total amount of options that you have. And R represents how many items that you are choosing from the group. So it's the chosen amount. For example, if you're picking 2 out of these 5 students, then R equals 2. Let's talk about a passcode. So if there's 10 that we can choose from, if there's 10 numbers that we can choose from for a passcode, then that means that N is going to equal 10. Now let's say that we want to choose a passcode that has only 4 digits, then that would mean that R equals 4. So we would write that as 10P4. And if you put that into your calculator, you can actually calculate how many possible passcodes there are for a 4-digit passcode. But we can also rewrite 10P4 as 10 factorial over 10 minus 4 factorial. You can plug either one into your calculator, but it might be just a little bit faster to plug in 10P4 instead. So if you put this into your calculator, you would get 5,040. There are 5,040 possible 4-digit passcodes. Let's do another example. Let's say that I have 7 books to choose from. That means that N equals 7. And I want to arrange just 4 of these books on my bookshelf. That means that R equals 4. Now this would also be a case of permutations, because for an arrangement of books on a shelf, the order of which the books are arranged at would matter, because having book A, B, C, D like this as an arrangement versus having book B, A, C, D, those are considered 2 different arrangements. So it's considered as permutations. So if I want to calculate how many possible ways there are of arranging 4 of these books on my bookshelf, then I would type in 7P4 in my calculator, and I would get 840. So there's 840 ways of arranging 4 books on a shelf out of 7 books to choose from. Okay, now let's talk about combinations. So, as I said before, for combinations, the order doesn't matter. The only difference between permutations and combinations is the fact that for permutations, order does matter, and for combinations, the order doesn't matter. So, for example, if we have A, B, C, D versus B, A, C, D, for combinations, that would be considered as the same arrangement. The only thing that would be considered as different for combinations is if you have an actual different thing in there. So A, B, C, D is considered as different than A, E, C, D. So let's look at the formula for combinations. The formula for combinations is NCR equals N factorial over R factorial times N minus R factorial. Okay, so let's do an example. A great example for combinations would be choosing students. So we got A, B, C, D, E, F. So we have 6 students. That means that N equals 6. And we want to choose 3 to be on a team. So that means that R equals 3. Okay, so we have 6 students and we want to choose 3 out of these 6 students. So we're going to do 6C3, which equals 6 factorial over 3 factorial times 6 minus 3 factorial. So we can plug either one of these into our calculator. We're going to get 20. There's 20 different arrangements. Now this number is significantly smaller than any of the numbers that we've seen for permutations. Why is that? That's because for combinations, the order doesn't matter, which means that we have less options to choose from. Because permutations would have said that choosing A, B, C as the 3 students is different as choosing BAC as the 3 students. However, combination says that these are the same. It doesn't matter. And yeah, it doesn't matter choosing student A and student B on a trip compared to choosing student B and student A on a trip, because it's the same thing. All you're doing is choosing 3 students from these 6 for a team. It doesn't matter which order you choose these students in because they're all chosen for the same team. So the order doesn't matter. Now let's do a different example for combinations. Let's say that we're having a fruit salad. So we have 6 fruits to choose from. So n equals 6. And let's say that we only want 4 fruits in the salad. So r equals 4. So we're gonna do 6C4, which equals 15. So we have 15 possible combinations of these fruits. Now the reason that we choose combinations for a fruit salad, if you have a fruit salad, let's say it's in a bowl, right? It doesn't matter if you choose fruit A and then fruit B versus if you choose fruit B and fruit A. It doesn't matter because you have the same fruits in the salad. These 2 bowls aren't considered as a different serving of a fruit salad. They're considered as the exact same thing because you have the same fruits and that's all that matters. It doesn't matter which order you put these fruits in. So that's why it's considered as combinations, because for combinations, again, order does not matter. Let's say we have the word mouse. How many different ways can we rearrange the letters in this word to make new words? It doesn't matter if the new word is actually a word or not. It's just like how many different arrangements do we have with the given letters for mouse? Oh, this goes back to the simple principles of counting, right? It would just be 5 factorial, which is 5 times 4 times 3 times 2 times 1. So we have 5 factorial amount of different ways to rearrange the letters from the word mouse. Now, what if we had a different word? What if we had a word that had letters that repeated? We have 1 and 2 O's. So how is that going to look? Because if we have, let's say that we have the spelling Roblox, and this is O number 1, this is O number 2, versus if we have the spelling Roblox again, however, all we did was swap the O's. We're not going to consider that as a whole different arrangement because it's not. Because the O letters, they're the same, so it doesn't matter if you switch them. So that's why we can't count those certain arrangements in. And this is where distinguishable permutations come in. So instead of doing 6 factorial, because there's 6 letters, we're going to do 6 factorial divided by 2 factorial, because we have two of the same O's. And let's say we had a word that had multiple reoccurring letters, as in like representation. So let's count what we have here. So for R's, we have 1, 2, looks like we just have 2. For E's, we have 1, 2, 3, 3 E's. We just have 1 P. We have 1 S. We have 2 N's, and then we have 2 T's, and then we have 1 A, we have 1 I, and we have 1 O. So that's good. In representation, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14 letters. So we're going to do 14 factorial. However, because there are so many of these reoccurring letters, we're going to do, for R, we're going to do 2 factorial. For E, we're going to do 3 factorial. N, 2 factorial, and then T, 2 factorial. So really what we're calculating here is 14 factorial over 2 factorial times 3 factorial times 2 factorial times 2 factorial. So let's plug that in our calculator. And okay, so this is a large number. I did not intend this, but we got 18162144400, and I'm not even gonna try to pronounce that number because I don't really care. So yeah, we have this much amount of ways to respell representation, but whatever this number is, it is going to be less than 14 factorial, that's for sure. Because we have these different reoccurring letters here, we have to put these over the 14 factorial because we don't count the rearrangement of 2 identical letters as a different arrangement because the difference isn't distinguishable, hence the name distinguishable permutations. So that's all I wanted to cover today. I hope you found this video useful, and I'll see you in the next one.